Now we are going to continue with the third lecture of the Alberto Elduque's course in composition algebras. Alberto, it's all yours whenever you're ready.
Thank you very much, Jose. So let's review a little bit what we did yesterday. We're talking about composition algebras. So we started with definitions. In the definition, there were some words with strange, like non-singular, multiplicative. Well, the non-singularity didn't affect much, in the sense that, remember that what we saw is that essentially a quadratic form is non-singular if the corresponding bilinear form is non-degenerate. The only exception to that is in case of a field of characteristic 2 and an algebra of dimension 1. So essentially we can forget about that because this is a trivial case. So we can assume always that the bilinear form that appears as the polar form of the norm is non-degenerate. So we have a non-degenerate bilinear form induced by the norm, and we had Hurwitz algebras are unital composition algebras. So we review all these things, and now I have corrected the minus signs that appeared yesterday that were not correct. Just by linearization of the multiplicative property, we get a couple of identities involving the norm, qualities involving the norm, that just are deduced from the multiplicative property by this process of linearization that I mentioned yesterday. And with that, we were able to prove some nice properties of these algebras. So all these unital composition algebras have an involution, x bar, which is obtained just by reflection with respect to the unity. So if x is orthogonal to the unity, then x bar is just minus x. Otherwise, it has to add this term. This is an involution. Also, and that was very important for the computations, whenever we use the polar form of the norm, we can move things from one side to the other. So we can move x from the left to the right, adding the bar, the involution. Or we can move y to the right, adding the involution. The algebras that appear may fail to be associative, but at least they satisfy a weak form of associativity. This is the alternativity condition. So these algebras are always alternative, and this means that they satisfy these two identities that appear on the screen. And finally, all these algebras are quadratic in the sense that the square is always a linear combination of 1 and x. Something like this appeared in the first talk this morning, where x squared was always a linear combination of 1 and x. And if the field has enough elements, this always gives a linear form and a quadratic form. In our case, the quadratic form that appears is the norm. It is the coefficient of 1. And the coefficient of x is given by minus the trace, evaluating the normal form in x and 1. Okay, so we had all these properties, and with these properties, we were able to deduce a few things. Proving these properties. And at a certain point, we consider this situation. We have a Hurwitz algebra, so a unital composition algebra, and we take a nice proper subalgebra. So by nice, I mean that it is unital, and the restriction of the polar form is non-degenerate in Q, in the subalgebra. And whenever we had this situation, we were able to show that if we take an element in the orthogonal complement, an element with non-zero norm, and we play with this element, it turns out, we prove a few things about that, and it turns out that the subspace obtained as the direct sum of our nice subalgebra and a copy of this nice subalgebra, just the multiples of this element in the orthogonal complement, multiples by elements of Q. If we take this doubling of Q, this is also a subalgebra. And the way that elements in this direct sum multiply and the norm of elements, well, are given by the same formulas that we used the first day to define octonions starting from quaternions. I mean, the real division algebra of octonions starting from the real division algebra of quaternions. In that case, alpha was -1. But apart from that, these are exactly the same formulas that we have been using. So whenever we have a nice proper subalgebra, inside our Hurwitz algebra, there is another subalgebra whose dimension is twice the dimension of the original algebra, and the multiplication and norm are given in these terms. Okay, so this is very important. And we made some computation that tell us that actually any proper nice subalgebra is associative. Okay, so this is also quite important. And moreover, the algebra that we obtain by doubling Q, the subalgebra that we obtain by doubling Q in this way is associative if and only if the subalgebra we have started with is commutative. So this Q plus QU is associative if and only if we start with a commutative Q. Okay, so we got some interesting properties, just playing a little bit with linearization of the multiplicative property. This is all we use. And so we prove that given any nice subalgebra, proper nice subalgebra, there is always a subalgebra whose dimension is twice the dimension of this algebra is obtained by doubling the subalgebra. Moreover, we have proved that if this happens, the subalgebra is always associative. And moreover, if this double subalgebra is associative, then necessarily the subalgebra we've started with is commutative. Okay, so all these things were proved just by using nice linearization of the multiplicative property and how the involution behaves with respect to the norm and these kind of things. So all are quite straightforward. Okay, so with this, we were able to assert this theorem. Now, today we are going to prove this theorem that tell us that any unital composition algebra, any Hurwitz algebra, over a field is either up to isomorphism, the ground field, or a two-dimensional commutative, associative, and nice two-dimensional algebra, or a quaternion algebra, which is an algebra obtained by doubling a two-dimensional Hurwitz algebra, or an algebra obtained by doubling a quaternion algebra. So in the third step, we double subalgebra that behaves as in the second step. And in the fourth step, we double a subalgebra, a quaternion subalgebra. And that's it. We cannot continue doubling. So in particular, the dimension of a Hurwitz algebra is always finite and restricted to 1, 2, 4, or 8. There is no other possibility. Okay, so let's prove this, and we'll see that with the things we did yesterday, this is very easy. Sorry. Okay, so the proof of this theorem, okay, if the dimension of our Hurwitz algebra is 1, that's it. This is a unital algebra of dimension 1 up to isomorphism is the ground field. So we are finished. Now, if the dimension is greater than 1, then immediately we don't have any problem about this non-singularity thing, that there was just one exception, and this exception happened in dimension 1. So if the dimension is greater than 1, we know that the polar 4 is non-degenerate. And in this case, we can always take an element which is not a multiple, a scalar multiple of 1, and that has trace 1, and the restriction of the norm to the subspace spanned by 1 and V is non-degenerate. Actually, if the characteristic is different from 2, this can be done very easily by taking first an element which is orthogonal to 1 with non-zero norm, and then adjust this element. If the characteristic is 2, one has to play a little bit with the norm, but we can always take elements of norm 1, of trace 1, sorry, and then adjust these elements so as to get that the norm is non-degenerate. So I leave this as an exercise. The only problem is in characteristic 2, but this is quite easy. An exercise. And then, well, the Cayley-Hamilton equation tells us how this V multiplies by itself. V squared equals minus the trace of V, which is 1, plus the norm. So if the norm is minus mu, then we know that V squared equals V plus mu times 1. So we have this subalgebra. We denote this subalgebra by K. And because the norm is non-degenerate here, the polar form of the norm is non-degenerate, this is a Hurwitz subalgebra of C. So if the dimension is 2, that's it. If not, we have a two-dimensional nice subalgebra of C. So if the dimension is 2, we have finished. If not, well, this is a nice subalgebra, K, that we have obtained so far. And now we take an element orthogonal to K with non-zero norm. And now we apply what we know. Every time we have a nice subalgebra, there is a subalgebra obtained by doubling this subalgebra in this way. So if the dimension is greater than 2, we can always obtain a subalgebra that is obtained doubling K. This is the notation that we use, the Cayley-Dixon doubling of K using the scalar beta. Okay, so if the dimension is greater than 2, we always have a subalgebra which is of this form. And this is a quaternion subalgebra. This is exactly what we did obtaining the quaternions starting from the complex numbers. So if the dimension is greater than 2, we always have a subalgebra which we know is associative because K is commutative. It is two-dimensional and therefore commutative. So we know this subalgebra is associative and has dimension 4. So if the dimension of our Hurwitz algebra is 4, that's it. This is the whole algebra. It is a quaternion algebra. If not, if the dimension is greater than 4, in the previous step, we have obtained a 4-dimensional associative nice subalgebra. So if the dimension is greater than 4, we can double this subalgebra and get a larger subalgebra. Okay. So we take an element orthogonal to Q with non-zero norm and use this element to double our subalgebra Q. Now, Q is associative. So that's fine. This is what we need. But Q is not commutative. So we know that this algebra is not associative. Because for a double algebra to be associative, the subalgebra we start with must be commutative. And Q is not commutative. So this subalgebra that we have obtained is associative. And the norm is non-degenerate in this subalgebra. And we also checked yesterday that any proper nice subalgebra of a Hurwitz algebra is associative. So this subalgebra we know is not associative. So it cannot be proper. It has to be the whole algebra. And we are finished. Okay. So if the dimension is 1, everything is trivial. If not, we can obtain a 2-dimensional subalgebra. If the dimension is 2, we are finished. If not, we can use this 2-dimensional subalgebra to double and get a 4-dimensional subalgebra. And if the dimension is 4, we are finished. If not, we have obtained an associative non-commutative subalgebra of dimension 4 that we can use to get a double algebra of dimension 8. And this cannot be associative. So it has to be the whole algebra, because proper nice subalgebras are always associative. So the dimension must be 8, and we are finished. We cannot continue. Okay, so that's the proof of the result. Okay, see. if the characteristic is not 2, then things are actually easy, because we can, the second step, the step of getting a two-dimensional subalgebra, is easier. It is exactly as the third and fourth steps. So things are a bit easier. So just with this argument, but in characteristic not 2, we get either the ground field, or in the second step, the two-dimensional subalgebra can be obtained by doubling the one-dimensional subalgebra that we have with the unit. So the second step is easier to state. So either we get the ground field, or a two-dimensional algebra obtained by doubling the ground field, or a quaternion algebra obtained by doubling a subalgebras in the second step, or a Cayley algebra obtained by doubling a quaternion algebra. And that's all. Because once we get here, this is not associative, so it has to be the whole algebra. Okay, now this is the natural question. And then what happens if we use the same formulas that we had before to double a Cayley algebra? And then the answer is that what we get is not a Hurwitz algebra. So the formulas are valid, but we lost the multiplicative property of the norm. So the new algebra is no longer a composition algebra. However, it has some nice properties. And in the talk yesterday by Svetlana Silina, well, she talked about these algebras obtained by applying the Cayley-Dickson doubling process after obtaining Cayley algebras. The new algebras that we obtain are no longer Hurwitz algebras, are no longer composition algebras. The norm is no longer multiplicative, but we have a norm. We have a Cayley-Hamilton equation of degree 2. So they are flexible, they are not alternative, they are no longer alternative, but they satisfy a weak version of associativity too. But what happens is that these algebras are more rigid. What do I mean by this? See, when we have a Cayley algebra, like in the first day, an octonion division algebra over the real numbers, and we have a quaternion subalgebra, we can use any element in the orthogonal complement to double this quaternion subalgebra. So we have a lot of freedom to choose the element U or L or whatever the name we use for that. And this means that there are many symmetries of these algebras. These algebras are very symmetric. Well, actually, the symmetries of an algebra are reflected in the oromorphism group. Justin McEnroy is explaining things about the oromorphism group of the axial algebras, how important these oromorphism groups or some subgroups are. Well, what happens up to the octonions, up to the fourth step, is that the groups of oromorphisms are quite nice and relatively big. If we continue doubling, we don't get composition algebras, we don't get Hurwitz algebras. We get some algebras that are interesting, and the study of zero divisors and things like that are quite interesting, but they are no longer composition algebras, and they are more rigid in the sense that the oromorphism group doesn't grow much. Actually, the connected component of the oromorphism groups of the new algebras is exactly the same as for Cayley algebras. So essentially, the oromorphism group doesn't grow much. And this is because we don't have this liberty to choose the element U in whatever way we want in the orthogonal complement. The new elements U that are used to double are essentially fixed. And these ideas appear perhaps a bit hidden in the talk by Svetlana Silina, but this is what happens. And the algebras that we obtain are no longer, these algebras are no longer composition algebras. They are interesting algebras, but they are less symmetric than these algebras. In a sense, the more symmetric an algebra is, the more beautiful it is. The symmetries reflect the beauty of what is going on there. Okay, so this is what happens in characteristic note 2. Things are a bit easier. Now, over the real numbers, the scalars that we use to double things alpha, beta, and gamma, well, this element U that we use to get the double algebra can always scale so that this scalar becomes over the real numbers either 1 or -1. And the classical real division algebras that we were talking about the first day are obtained, well, the complex numbers is just after isomorphism, the algebra that we obtain by doubling R with the scalar -1. The Hamilton algebra of quaternions, the real division algebra of quaternions, is obtained by doubling the complex numbers with the scalar -1. And in the same way, the real division algebra of octonions is obtained by doubling the quaternions with -1. Okay. Actually, over the real numbers, we can double with 1 or -1, that's all. And if we double with 1, we obtain algebras with isotropic non-zero vectors, and we will talk about them later on. Okay. Well, the history of this theorem, well, the first day I told you a little bit about history, I told you about the discovery of quaternions, octonions, and so on. But a real classification took more years, and actually Hurwitz proved this theorem in the real case with positive definite norm. Later on, a few years later, it was proved essentially in characteristic 0. And over the years, this was extended to arbitrary characteristic and so on. So in characteristic different from 2, this theorem appears, I believe, for the first time in a paper by Jacobson, and 1 year later, it was proved also in characteristic 2 by Van der Vliet and Springer. But essentially, the theorem was there in the air for many years. Okay, so now we have seen that any unital composition algebra, the Hurwitz algebra, is obtained doubling algebras of small dimension. Well, there is a problem in characteristic 2 and dimension 2, where the two-dimensional algebras are not obtained by doubling the field, but apart from this problem in dimension 2 and characteristic 2, essentially all these algebras are obtained using the Cayley-Dickson doubling process. But now the problem is, how do we check if 2 of these algebras are isomorphic? Because we have a lot of liberty, a lot of freedom in choosing the scalars to make the doubling process, and so on. So how to check when do we get isomorphic algebras? And the result is nice, because everything depends on the norm. 2 Hurwitz algebras over a field are isomorphic if and only if their norms are isometric. So the problem restricts to a problem in linear algebra, whether these 2 quadratic forms are isometric or not. So the isomorphism class is determined by the isometry class of the norm. So this is reduced to a linear algebra problem. And actually, the proof depends on linear algebra. Well, to begin with, any isomorphism of Hurwitz algebras is an isometry of the corresponding norms. And this is because we have the Cayley-Hamilton equation, this equation of degree 2. So if we have an isometry, because of this equation, it must preserve the coefficients that appears in this equation. And one of the coefficients is the norm. And that's the idea. So using that, any isomorphism is always an isometry of the corresponding norms. And now, in order to get the converse, whenever we have that the norms are isometric, how do we get that the algebras are isomorphic? Well, using the Cayley-Dickson doubling process together with Beat's cancellation theorem that tell us that whenever we have 2 vector spaces with quadratic forms, and we have subspaces with isometric restrictions, then this isometry can be extended to the whole space. So we can extend, using the Cayley-Dickson doubling process, we can extend the isometry. And using the Beat's cancellation theorem. And this is all we need. So this is very nice. We know how to describe all the algebras. Essentially, they are all obtained by doubling smaller algebras. And we have a criterion to check whether two of these are isomorphic in case we use different parameters to get it out. Okay. So this is about Hurwitz algebras. And Hurwitz algebras, remember, are the unital composition algebras. So now, what happens if we forget about the existence of an identity element? If we deal just with composition algebras, and we forget about these algebras being unital? Well, the result is that if a composition algebra, not necessarily unital, if the dimension is finite, then the dimension must be 1, 2, 4, or 8. There are no other possibilities. Okay? But for Hurwitz algebras, what we know is that they are finite dimensional, and the dimension is either 1, 2, 4, or 8. For non-unital composition algebras, if the dimension is finite, it has to be 1, 2, 4, or 8. But the dimension can be infinite. Okay? So how do we prove this? And this is quite nice. Well, so we start with a composition algebra C. And we take an element of non-zero norm. The norm is non-degenerate, so there are elements with non-zero norm. A. So we have this element A. Now take the element U, which is A squared divided by the norm. Okay? When you take the norm of this element, the norm of U, well, when the norm is quadratic, so this scalar gets out a square of the norm. So we get 1 over the square of the norm of A times the square of the norm of A. So this element has norm 1. Okay? Now we use this element of norm 1 to define a new multiplication on the algebra C. And this is called the Kaplansky string. So C, we have our multiplication, which is denoted by juxtaposition in C. This is a non-unital composition algebra. And now we define a new multiplication on the same vector space. But the new product of elements X and Y is given by this formula. Well, in this formula, L sub U is the left multiplication by U, and R sub U is the right multiplication by U. So, okay, I take the element X, and I apply the inverse of the right multiplication by U to X. I apply to Y the inverse of the left multiplication by U, and then I multiply in C the two elements that I get, 1 and 2. And I perform the multiplication in C. Okay? Okay. C. Since the norm of U is 1, the left multiplication by U, because of the multiplicative property of the norm, is an isometry. The right multiplication by U is an isometry. So I'm applying isometries here and here. So the norm of this element is the same as the norm of X, because the map that I'm applying preserves the norm. The same happens here. The norm of this element is the norm of Y, because I'm applying an isometry. So the norm of X diamond Y is the norm of this product. Well, the norm is multiplicative in C, so it is the norm of the first element times the norm of the second element, but the norm of the first element is the norm of X because we are applying an isometry, and the same in the second, for the second element. So the norm is also multiplicative for this new multiplication. So with this new multiplication, C is also a composition algebra. But now see what happens when we multiply U squared times X, but with the new multiplication. Okay, so instead of X, I put U squared here. Well, if you apply the inverse of the right multiplication by u to u squared, what you get is u. So here you get u. And now, instead of y, you put x. So here you write x. So you take x, you apply the inverse of the left multiplication by u, and then you left multiply by u. So the left multiplication by u and the inverse cancel, and you get x. So u squared diamond x equal x, and the same in the other direction. So see, this means that the diamond multiplication is unital. And the unity of this diamond multiplication is u squared. So, summarizing the argument, what we have proved is that if we start with a finite dimensional composition algebra, and we are able to find an element of norm 1, that's easy. Now, once we have an element of norm 1, we can deform the product, we can twist the multiplication to get a new multiplication in such a way that this new multiplication behaves nicely with respect to the norm, in the sense that the norm is multiplicative with respect to the new multiplication, but this new multiplication is unital. We have a unity element, and the unity element for the diamond multiplication is u squared. So this is a Hurwitz algebra. It is a unital composition algebra. And we know that the dimension of any Hurwitz algebra is 1, 2, 4, or 8. So that's it. The dimension is 1, 2, 4, or 8. Okay. So, and this is the Kaplansky's trick that allows us to pass from non-unital composition algebras to unital composition algebras, as long as the dimension is 5. Okay. And actually, Kaplansky, after realizing these kind of things, that he was able to move from non-unital composition algebras to unital composition algebras, he thought that probably any composition algebra, the dimension of any composition algebra should be finite, and therefore 1, 2, 4, or 8. But no, there are infinite dimensional composition algebras. Let me show you perhaps the simplest example that has some other interest. Okay, this example is 1960 by Urbanic and Wright, and the idea is the following. Take any bijection from n cross n into n. For instance, since any natural number, I start the natural numbers with 1. Okay? Since any natural number is uniquely written as a product of a power of 2 and an odd natural number in a unique way because of prime factorization, this is a bijection. By the way, this kind of bijections show that the countable union of countable sets are countable. Okay? And this kind of things in set theory. Okay, so you take a bijection like this, and this is always very surprising. The first time that one sees these kind of things is very surprising because it tells us that the number of elements in this Cartesian product equals the number of elements here. This set that looks much larger than the natural numbers, actually it has the same size. There is a bijection. Okay, okay. So take this bijection and now take a field of characteristic node 2 and take a countable basis of this, take a vector space with a countable basis. So we have this basis and define a norm imposing that this basis is an orthonormal basis. So the norm of any of these elements is 1 and they are all orthogonal. Different elements are orthogonal. Okay, and now define a multiplication in this algebra using this formula. So for instance, if you multiply u sub 2 times u sub 3, well, you get u of phi of 2, 3. So you apply here n equals 2, so you get 2 here, and 3, so you get what, 5, so u sub 10. The product of the second element of the basis and the third element in the basis is the 10th element in the basis. And so with all the elements. And now this is an exercise for you students to check that this is a composition algebra. So the norm of the product is the product of the norms. See, this is clear for basic elements because all have norm 1. And now using the orthogonality, that they are all orthogonal, it is very easy to get that the norm is multiplicative. Okay, so this is an example in infinite dimension. Actually, there are examples of infinite dimensional composition algebras of arbitrary infinite dimension. You take any infinite cardinal, take a vector space over an arbitrary field with dimension given by this cardinal that you have chosen, and one can define on this vector space a multiplication and a norm that gives you a composition algebra over with this vector space and this multiplication, and even composition algebras which are not unital, but have a unity on the left. So there is one element that multiplied on the left by any other element gives this other element. So it's the unity only on one side. The left multiplication by this element is the unity. So even imposing one-sided identity element, you can get many examples. Actually, when I got these examples with my former student Perez Izquierdo, the first thing I did was to send these examples to Kaplansky. And he replied very politely and very surprised of this amount of examples. Okay. Now, let's move to these isotropic Hurwitz algebras. So, this means just that being isotropic means that the norm represents 0. This means that there is a non-zero element in the algebra such that the norm is 0. See, whenever we have any quadratic form of dimension at least 2 on a vector space of dimension at least 2 over an algebraically closed field, this quadratic form always represents 0. There are always non-zero elements such that the norm, the quadratic form applied to these elements gives 0. Okay, so if we want to see what's going on with Hurwitz algebras over algebraically closed fields, well, over algebraically closed fields, except in dimension 1, the algebras are isotropic. There are always non-zero elements with 0 norm. Okay, so that's important if we want to check what happens over algebraically closed fields. And I need a specific basis of these isotropic Hurwitz algebras for next day. So this is important. And the goal is to check that if we impose that the norm of a Hurwitz algebra is isotropic, then there is only one possibility up to isomorphism in each dimension. Dimension 2, 4, or 8. Dimension 1, the norm is non-isotropic, anisotropic. But in dimension 2, 4, or 8, there is only one possibility. Now, see, this is related to a question of the first day. See, take the algebra of 2 by 2 matrices over a field. Okay, this is an associative algebra. We have the determinant. The determinant of a 2 by 2 matrix is given by a polynomial of degree 2. So it is a quadratic form. And it's easy to see that it is a non-degenerate quadratic form. And you all know that the determinant of the product of 2 matrices is the product of the determinants. And you know that there are non-zero matrices whose determinant is 0. Okay, so 2 by 2 matrices with the norm given by the determinant form an example of an isotropic Hurwitz algebra. It has dimension 4. The dimension has to be 1, 2, 4, or 8. In this case, it is 4 because it is associative. 2 by 2 matrices, the product is associative. So there you have the first example of an isotropic Hurwitz algebra. Well, I want to prove that this is the only example in dimension 4 up to isomorphism. So if you take any 4-dimensional isotropic Hurwitz algebra, it is isomorphic to the algebra of 2 by 2 matrices with the determinant as the norm. Okay? So this is the goal, to check that there is only one possibility in each dimension. Actually, I will essentially prove it in dimension 8 because in other dimensions it's easier. And so once you see what happens in dimension 8, everything follows in other dimensions. Anyway, the first thing that we have to do is to look for idempotents. Well, idempotents are very important. You've seen in the course by Justin McEnroy how, well, the axial algebras are defined in terms of certain idempotents of the algebra. Okay, so we are going to look for idempotents, idempotents other than the unity. We are dealing with Hurwitz algebra, so unital algebras. So we are going to look for idempotents other than the unity. And that's easy. See, we start with a non-zero element with zero norm. So take an element A like this. Now, since the norm is bilinear, it's quite easy to find an element such that the norm applied, the polar 4 applied to A and B bar is 1. Now, remember that we can move things to the other slot, adding a bar. So we can move B bar to the left, adding another bar, but 2 bars is the identity. So the fact that the norm of A comma B bar is 1 is the same as the fact that the norm of AB comma 1 is 1. Okay, because we can move to the other side. Also, the norm of AB, of this element AB, the norm of this element, well, the norm is multiplicative, and the norm of A is 0. So it is 0. Now, we have Cayley-Hamilton equation that tells us that the square of any element equals the trace times this element minus the norm multiplied by 1. But the norm of this element, AB, is 0. So Cayley-Hamilton equation tells us, and the trace is 1. We have this here. So Cayley-Hamilton equation tells us that this is an idempotent. Okay. So in an isotropic Hurwitz algebra, it is very easy to find idempotents. One starts with an element of norm 0, a non-zero element of norm 0, and then use the bilinearity to get, and the non-degeneracy of the polar 4 to find an element like this, B bar, and then one moves to B, and the element AB is always an idempotent. Okay. Now we have an idempotent of norm 0. Now, if you think about it, this element is also an idempotent. When you take the square, you get also this element. Every time you take an idempotent in an algebra and you take 1 minus this idempotent, you get another idempotent. And the product of E2 and E1 is 0. Because whenever you multiply 1 minus E1 by E1, you get E1 minus E1 squared, which is E1. So you get 0. So these are orthogonal idempotents. By orthogonal idempotents, I mean idempotents that multiply giving 0. So I have E1 and 1 minus E1, which is E2, and these are idempotents. Now we have a 2-dimensional subalgebra, K. And you can check easily that the norm restricted to this subalgebra is non-degenerate. So this is a nice proper subalgebra, and we can apply Cayley-Dickson doubling process. And we can take, therefore, the orthogonal complement and choose suitable elements in the orthogonal complement. So now take any element in the orthogonal complement. And see, let's compute the trace. The trace is the element plus the conjugate element. Well, the trace, as we know by now, equals the norm applied to x to this element, comma 1. I can move things to the other side with a bar. E1 bar is E2, and X is orthogonal to E1 and E2, so this is 0. Okay, so for any element in the orthogonal complement to K, we have that the element is orthogonal to E2, 0. In the same way, it is orthogonal to E1, and therefore it is orthogonal to 1, and therefore the conjugate equals minus X. So we have all these properties, and now the conjugate of X times E1, remember, this is an involution. So this is E1 bar times X bar. E1 bar is E2. X bar is minus X. So we get that for any element in the orthogonal complement to K, E1X is the same as XE2. And in the same way, you can prove that E2X is the same as XE1. Okay, so we can move the idempotence to the other side, changing the idempotence. Okay, actually, this follows from a lemma that we already used before. Okay, so now we're going to see something that I call the phase decomposition. The phase decomposition is once we have an idempotent, usually this idempotent splits the algebra into nice subspaces. This appears constantly in Justin McElroy course, because we take idempotence, the axis, and we split according to the eigenvalues of the left multiplication by this idempotent. Well, in general, when we have idempotence in algebras that are least power associative, we have decompositions attached to these idempotents. So we have two idempotents, orthogonal idempotents, E1 and E2. And now if you take an element which is orthogonal to K, well, I apply 1. And now you look at what happens with these elements. And the first element multiplied by E1 on the left, well, since E1 is an idempotent, leaves the element invariant. While the second is invariant under left multiplication by E2. The first element, if you multiply on the right by E2, well, we know that we can move idempotence to the other side by changing the idempotent. So we get E1x. So the first element, E1x, satisfies that whenever we multiply by E1, we get the same element, and the same when we multiply by E2. And then these two extra properties are proved in the same way. E1 can be moved to the other side. This is E2, but E2, E1 is 0, and therefore we get 0. Okay, so I'm going to be a bit more quickly than these previous days, just checking computations a little bit with the things we have been doing so far. One gets that the element E1x belongs to this subspace U, and the second element belongs to this other subspace. The intersection of these two subspaces is clearly trivial, and any element is a sum of an element in the first subspace and the second subspace. So this means that the orthogonal complement to K splits as a direct sum of this U and V. Okay. And now what I want to do is to check. So see, now we have that the whole algebra, the isotropic Hurwitz algebra C, consists of K, which is the direct sum of the subspace spanned by E1 and the subspace spanned by E2, plus the orthogonal complement, which is the direct sum of U and V. So we have a splitting of the whole algebra, which is more or less similar to the kind of splittings that Justin is using. The only thing is that Justin is dealing with commutative algebras, and we are dealing with non-commutative and even non-associative algebras. So things are a bit more involved here. But anyway, we have a nice splitting of the algebra. And now we compute things to see how the elements in this U and V behave. And it turns out that for any element in U, the norm is 0 because of the multiplicative property of the norm. The same happens with the elements in V. So all the elements in U have trivial norm, 0 norm. The same with the elements in V. But the direct sum of U and V is the orthogonal complement to K, and there the norm is non-degenerate. So whenever we have this situation, the norm must match these two subspaces. So both U and V are totally isotropic subspaces. This means that the norm of any element in each one of these subspaces is 0, and therefore necessarily they must have the same dimension and be paired by the norm. So the dimension is equal. So if the dimension of C is 2, well, if the dimension of C is 2, C is spanned by the two orthogonal idempotents, and that's, we are finished. If the dimension is 4, the orthogonal complement has dimension 2, so they must have dimension 1. And if the dimension is 8, K paired has dimension 6, so they must have dimension 3. And now the next thing to do is to check how these subspaces behave. And see, this is relative. What we are going to do has the same flavor as what Justin is doing with the compositions. He has these fusion rules that tell us how elements in different pairs components multiply. So, well, here we have our algebra split into first idempotent, second idempotent, subspace U, subspace V. Now we know how the idempotents multiply and how they relate with U and V, but now we have to check how U and V are related, how the multiplication of elements in U looks like, what the multiplication of these elements look like. The same with elements in V, how to multiply elements of U and elements in V, and we want to get all this. But I guess it is time for questions and comments, because there are some details I want to be more careful. So we'll start from here tomorrow. So if you have any questions, I will be happy to try to answer.
Thank you very much, Alberto.
Thank you.
Very nice. So are there any questions? Tiago? Applause. Okay.
Yes, Svetlana has a question, I believe.
Okay, go ahead.
Yes, thank you. Professor Elduque, I study Cayley-Dixon algebras, and they usually begin with a field and then use the Cayley-Dixon process many times of arbitrary dimension. And if we take the first field of characteristic 2, then we obtain a bad algebra since it is commutative and associative, but this is not interesting. But what happens if we consider this algebra, which is the composition algebra of dimension 2 with characteristic 2, and then use the Cayley-Dixon process not twice, but 3 or more times? Has it been studied?
Yeah, very interesting question. First of all, in the proof of the generalized Hurwitz theorem that I've mentioned, dimension 2 is different, because in general, the two-dimensional case is not obtained by doubling.
Yes.
So if we apply the Cayley-Dixon process as it is, starting with the ground field in characteristic 2, we get other types of values. The question is that the norm is singular for this value. So they are not compositional, but the norm is singular, but it has the multiplicative property.
Yes.
So that's the problem. But the kind of algebras one obtain are quite different. For instance, if you start with a field of characteristic 2, and you take any, let's say, purely inseparable field extension of degree 2 of the ground field, well, you may get algebras of many different dimensions, any power of 2 dimension. And this is, these are algebras obtained by the Cayley-Dickson Downing process. All of these. So one can obtain fields and field extensions of the ground field of any arbitrary degree being a power of 2. So the kind of algebras that appear is quite special. If in the definition of composition algebra, I define non-singularity in a different way,
Yes.
then one gets all these kind of algebras. But these kind of algebras are commutative, associative, and are very different from
yes, I know.
Yes, but they are quite different. Yes.
Yes.
But yes, this is. But the difference is that the norm is singular.
I know,
according
but
to our definition of singularity.
This ordinary Cayley-Dickson algebras are studied when characteristic is not 2, and they are the same as when we start with the algebra of dimension 2, because this algebra of dimension 2 is isomorphic to Cayley-Dickson algebra if the characteristic is not 2. But what happens if the characteristic is 2 and we start with this algebra, which is composition, and the norm is non-singular, and then apply the Cayley-Dickson process, say, 3 times? We have a 16-dimensional algebra, which is not an ordinary Cayley-Dickson algebra. Has it been studied?
Yeah, it may be a field. There appear many kinds of algebras there. They are quadratic and quadratic, commutative, and associative algebras. And I guess not much more than that can be said.
Thank you.
But this family includes fields, but only purely inseparable field extensions. So it includes some interesting objects. But that's why in order to deal with the real Hurwitz algebras in characteristic 2, here the characteristic of the field can be 2, we must work in a different way in dimension 2. Otherwise, one gets the algebras you mentioned, and these are other algebras. And
yes, thank you.
You're welcome.
We have one more question of the norm.
Yes, thank you. So more of a curious and less deep question. What would happen if, say, we take over a type of octonion algebra over the complex numbers, and then consider it as a real vector space?
Yes. Okay. First of all, if you consider the Cayley algebra over the complex numbers,
yes,
this is an example of isotropic Hurwitz algebra over the complex numbers. So there is only one possibility that we will see tomorrow, exactly the multiplication table and everything. If you consider it as a real algebra, it's no longer a composition algebra, because the norm takes values in the complex numbers.
Yeah, okay.
It is not a quadratic 4 over the real numbers.
Yes, yes, yeah.
And there is no way of adjusting things. There is no way. You cannot. Yes. It can never be considered as a Hurwitz algebra over the real numbers.
Yes. And the other question is, you talked about the 2x2 matrices as an example of isotropic Hurwitz algebras with the determinant as a norm.
Yes.
Which part fails under this? in the same setting if I consider bigger matrices?
Yeah, I'm very happy about that question. Okay, consider 3 by 3 matrices.
Yes.
We know that the determinant of the product is the product of the determinants, but the determinant is a polynomial of degree 3 in the entries. It's not a quadratic form. It is a cubic form.
Ah, yes.
And that's why it is not unital compositional. There are very interesting algebras that have a cubic norm that permits composition.
Yes.
Okay? But these are not compositional algebras. But there are algebras with these properties, not just 3 by 3 matrices.
Yes.
And if you take 5 by 5 matrices, the determinant is a quintic polynomial.
Yes.
So, yeah, it's a different thing, but this is what happens. Yes.
Yeah, thank you very much.
You're welcome.
So we need to move to the next lecture now. So thank you, Alberto, again. Thank you very much.
Thank you. Thank you for your attention.